Okay guys, welcome to a presentation on functions. Like we said, this is a continuation. We're discussing the concept and the basic terminology involved here. Then we'll see different types of functions later. Is that fine? Okay. So let's start this way. Like we said before, a function is simple an input-output system. We discussed that. But being an input-output system in our situation, our functions are going to be mathematical functions, which are going to be represented by mathematical expression. Like for example, this would be a function y is equal to 2x plus 1. But before you say something is a function, you must be sure that whenever you're given an input, that expression will give you a result which is unique, meaning one and the only one. Now, once you've got a function, a mathematical function like this, what is important is to know how to evaluate the function. How to evaluate the function. In this case, let's say we've got this function as 2x plus 1. We want the value at 2. What we simply do there, we write exactly like this. Note that in the place of x there, the function, what is sitting in the place of x, what is sitting there is 2. So what does that mean? This 2x means 2 times x. So f at 2 will mean 2 times 2 plus 1. And that will give us 2 times 2 is 4 plus 1 is 5. So we say the value of that function at 2 is equal to 5. Is that fine, guys? So I would invite you to attempt the following evaluations. Like evaluate the function at minus 5. Do it yourself. Now, tell me the answer. Evaluate the function at minus 5. Okay? I've given you enough time. Let's see. What's the answer at minus 5? What's the value of the function at minus 5? It says minus 9, which means we just 2 here, put minus 5 there where there's x plus 1, and you get that as minus 10 plus 1, which is going to be equal to minus 9. And then let's evaluate the function at delta x. This is just anything. Let's say we're evaluating it, the value of function at p, the value of function at delta x. What would be the value of function at delta x in this case here? Can you write it down, please? Quickly. You mustn't take a lot of time to do that. Let's see. Who can read me your answer? Who can read me his or her answer? Tate? What have you written? 2 delta x plus 1. So we just write here 2 brackets delta x plus 1. So this gives you an idea that what did you do if you are given anything here? It doesn't matter what you are given here, but you are evaluating according to the law of formation there. You would say 2 times the argument times 1. All together? Okay. So then I said for a function, for anything to be a function, it must be that the output is unique. So if I give you a function in terms of pairs like this, I don't care what is the rule of the function in this case. I'm just giving you a function in terms of pairs like this. It will be the following. If I give you x, it will be paired with the value of the function f at x. So we don't really know what's the function here, but we want to check whether this is a function or it's not a function. The value of a given input must be unique. Is this a function? R. Check R. Is R a function? I was saying here now, if a function can also be given as kind of ordered pairs in this order, that the first value is the input, the second value is the output. So I give it as x, f at x. So, but considering that we say, for any kind of relation like this with a function, the output must be unique. I'm saying, check R here. Check R. Is R a function or not a function? It is a function. You will say it's not a function only when you see some x0. Let's say x0 here. And another x0 there. Maybe this x0 appearing with p0. And the x again, the x0 appearing with the p1. What would that suggest? It would suggest that for x0, there are 2 possible outputs. P0 and the P1. Altogether. Are you understanding? If there was a situation like this, then we would say there's not a function. But here, we don't see any coordinate, any first coordinate appearing twice. So this is, yes, this is a function. Number 2, S. Look at S. Is S a function or not a function? It's not a function. Then you must tell me what makes S fail to be a function. What makes X fail to be a function? Which one? Tell me, name the input. 1 can output 4 and 1 can output, or 1 can output 17. That makes it not a function. Altogether. Good. Then that's that. Then let's look at the table. That's another way of giving a function. You can also give a function as a table of values. There is the table. Input is X, output is Y. What do you say about that? Function or not a function? Function. Because we don't see any value which is appearing twice as X. Altogether? Okay. Now, let's come to the next part here. This is what we said we can represent a function diagrammatically as an action from one set to another set. Is that right? Is that what we discussed, isn't it? Yes. That's exactly what we discussed. Then let's go further with that. Then when we look at this, in this case here, we would say X is the domain. X is the domain. So in this case here, X would be what you can call the domain of F. That's what we can say. Or the same thing, we can denote it this way. We can just write D sub F to mean the domain of F. What is the domain of F? It's basically the set of values such that Y equals to F of X is something which makes sense. Like in this case, we're basically dealing with real numbers. So if we're evaluating X is a real number, we must expect that Y there is a real number, a defined, a definite number, not something like 1 over 0. If the value here gives something like this, then whatever value you put there will not be in the domain of the function. Am I making sense? Yes. Okay. Like for example, if you take a real number minus 1 and you do that, this we can say it's not in the domain of the square root, because the square root is not going to deliver you anything there, a real number. Altogether? Yes. Okay. So we would say minus 1 is not in the domain of that. So please, these terms, you must understand them and understand how to use them. And if I give you a function later with a defining expression, you must be able to say this value and that value is in the domain and this one is not in the domain. Altogether? Okay. Then we've got what we call a range. We've already done the evaluation of a function. We've already done evaluation of a function. What is the image of a function? We can write again the image of F, or sometimes people use what we call range. Let me add one word here. Basically, synonym to that in this context. Range of F. What is the range of F? In this case, the range of F would be this set of values Y equals to F of X such that X is sitting where? In the domain X. Altogether. You understand what I'm saying there? It will be the values Y such that the value of Y is kind of an image or a value of some X which is in the domain. That we call that range of F, we call that domain of F. This kind of notation, we're still going to look at it, you must know how to write it correctly and be able to read it correctly yourself. Is that right? So, okay, let's move on. Our functions are given this way. Y is equal to F of X. Please notice that here, X comes from the domain. We normally call that independent variable. Independent variable. In other words, X can just change values within the domain and give us a corresponding value. So we say it's a variable. This word also variable, to make it clear there. Is that right? And then the value of y will basically depend on what x is. Then this variable here is going to be called the dependent variable. Dependent variable. So a function basically is a relationship between what? Between an independent variable and a dependent variable. Are we together, guys? Okay. Then we name our functions this way because in general, in mathematics in general, we plot functions, graphs of functions where on an x, y system of coordinates. System of coordinates. Which is exactly this. These x's here, the horizontal axis basically would be sort of enumerated here with numbers 1, 2, 3, obviously starting here from 0, which is the origin of the system, going up, and also negative in that way. And all the points in between there representing what? Real numbers. Altogether. So also this one is also a real axis, and then we've got that going that side, and we've got also this graduated like that with no one. So if we were to plot a graph here, basically a graph of function will be generally something more or less like this. And then when you look at a point there, you must see that that point is a pair x, comma, f at x. You must never overlook that. Am I making sense? Yes or no? And then if I draw a horizontal somewhere there, and they say this value here is, let's say, some C0. Let's say that value is some C0, a constant. Then here, what would this indicate? It will indicate that the value of the function and the C0 are equal. So that I will take that as f of x equals to C0. By so doing, for any function, by so doing, you basically come up with what we call an equation. And since we know C0 is a constant given there, then we need to determine the value of x, which will be somewhere there on the horizontal. So then we'll be solving here for x. So message, any function or any type of function will give place to a certain type of equation associated with that type of function. What did I say? I said any type of function during this kind of process will always give place to what? To a certain type of an equation associated with that type of functions. Altogether. So if we deal with exponential functions, there will be exponential equations. We deal with trigonometric functions, there will be trigonometric equation. We deal with quadratic functions, there will be quadratic equations to solve. Are we together, guys? Good. Let's move on. Then the next slide is the following. Composite functions. So here what we are doing basically, we are doing some kind of interaction between two functions, like with numbers. If we've got 2 and 3, we can have some interaction between 2 and 3 in many different ways. We can have 2 multiplying 3 to give us 6. We can have 2 added to 3 to give us 5. We can have 2 divided by 3 to give us something else. That is interaction between numbers. So now given functions, like let's say given 2 functions, you can have some kind of interaction between 2 functions. So in this case, what we have here? We have here f acting between x and y, and what is within that dotted kind of region there, within that, that's what we call the image of f. Now the question is, if we've got a function from x to y and another function from g to z, the question is there a function straight from x to y? The answer is yes, but under a certain condition. It must be that the domain of this g is within where? The image of F. Do you see that? It's not the domain of G must fall within the image of F. So if that happens, then you can have a new function here which you can call H, and this is going to be H of X. That function would be a function which first of all calls upon the action of F, which will be F of X, followed by the action of G, and then we write it like that. G after F. What I put in bracket there, we say G after F. What this says basically says that you evaluate F first, then evaluate G on the values of F. Am I making sense, guys? For G, you'll have to take values of F, evaluate them, and land somewhere at Z. And this kind of a function is going to be called a composite function. Now it's a composite of F and G. And this is read as G after F. Example, here we are. We're given F, this is F, and this is G. Sorry for that. Sorry, this is F, let's call this one G. That was my typing error there. And now let's see. Which means this expression is somewhere there in between there. And this expression is somewhere here. So let's do H, composite H. We'll say H of X. We'll work with this expression. This is a good one for calculations. This is a good one for calculations. We'll do this. We'll write G. And write G at F of X. That means G at F of X. So what I'll do, next step, what I'm going to do, we're going to write G again. And then replace F of X by its expression. What the expression of F of X is 2x plus 1. So we write here 2x plus 1. Guys, if I'm not making sense, you stop me immediately. Am I making sense?
Yes.
Okay. So then what does G say? G says whatever I'm holding as an argument, this part of the function here, for example here, the argument of G is X. Here, the argument of G is F of X. In other words, that thing in the brackets of in the function, we call it the argument of the function. This is the argument of G. But here the argument of G is a simple X. So please know what I'm saying. When I say argument, I'm saying what the function is picking to act upon. Am I making sense? Okay. So now when we come here now, we have got to speak the language of G. What does the language of G say? G says whatever I pick, I square it. After that, I subtract the 3 multiple of it, and then subtract 1. So what's going to happen here? This is going to say 2x plus 1 squared minus 3 in brackets 2x plus 1 minus 1. So our next step is to do all these calculations and simplify and make sure that we get a simpler expression. So let's try to do that for now. Basically what we're going to use here, we're going to use our usual story a plus b squared, which is a squared plus 2ab plus b squared for this term. So if we do that, we'll say a squared here, which is going to be 4x squared, which is a 2 squared multiplied by x squared, plus 2 brackets 2x brackets 1. That is for that only. Then minus 6x minus 3 minus 1. Simplifying that, what are we going to get here? We're going to get 4x minus 6. So this is going to give us what? 4x squared. Here minus 6 plus 4x, which is going to give us minus 2x. And then minus 3 minus 4. Minus 3 minus 1 going to give us minus 4. That is the composite function. Yes? Plus 1. Or here? Okay, there's a missing plus 1 here. Thank you for that. There's a plus 1 missing there, isn't it? So if there's a plus 1 missing there, this plus 1 and the minus 1 will give us a 0. And then we're left with what? Minus 3. Good. Okay, please, thank you. Look out of that, because I might be rushing in. Sometimes I overlook some of the things. You must correct me, and that will show me that you are following what we are doing, isn't it? So what you have here is minus 3, isn't it? Minus 3. Thank you for that. So now what you can do now, I want you to invite you to do this thing on your own. Pick a 2. Evaluate there, F, come here. I think you're going to get a 5 inside there, isn't it? And then evaluate 5, get there. Then pick a 2 now using what H? I'll leave that for your homework to do that. Pick a 2 using your H, in other words, this expression, and see that you get the same thing. All together? Okay. Please leave the calculator alone for now. Then let's do the other way around. Let's suppose this fixed function which was acting here was H, was G, and after that it was F. So what we do have there? We will have a new function called K of X, which is now F after G. F after G of X, which simply means F evaluated at G of X. In other words, we assume in this case that the domain of F is a subset of the image of G. That is very important. So then what we're going to do here, we're going to now say F action of G. Where is action of G? There it is. X squared minus 3x minus 1. All together. Then after that, followed by the action of G. Action of F. Action of F says whatever I pick, I multiply by 2. So this is going to be 2 brackets x squared minus 3x minus 1 and add 1. And then what happens then? Then this is going to be 2x squared minus 6x minus 2 plus 1, which will give us what? 2x squared minus 6 minus 1. Are we together? If you look at this, minus 6x, sorry, yeah, minus 6x there. If you look at this, 2x minus 6x minus 1 is different from that. All together? Yeah. So now, observe something here. Unlike in working with numbers, 2 times 3 is equals to 3 times 2. But when you compose functions, f after g of x is not in generally g after f of x. In general, you get two different functions altogether. We will see later when do we get the same function. We will see later when do we get the same function. So guys, what I'm going to ask you to do now, you got your compilation of exercises, do these similar examples. You are going to be tested and checked if you have done this practice. All together? Okay. Then let's go further. Any questions at that point? Sorry? No questions. Then let's go further. So now, let's do this way. Now I want to look at inverse function. Guys, in this case, we're in the presence of a function from x to what? To what? To y. Again, inside y here, we'll be having something which will be the image of what? Of f. Because we can't guarantee that the whole set y is an image of f. So at least you can say at least once a subset is an image of f. And then the question is now, is there a function which you can run from y to what? To x. If you look at this, it basically means that x was an input and it gave us an output what? Y. But if we now run a function this way, it will mean that y is an input and it will give out what? X. So basically we're asking that if we've got a process f from x to y, can that process f be reversed? Are you understanding? Like the same thing. If you're coming from home to school, can you reverse the process? Yes. Otherwise, if you can't reverse the process, you don't know where you're going to sleep today. You must know the way to school and know the way back home. Altogether. You understand what I'm saying? Yeah, that's the story. So obvious, if this such a function is there, it must be running from what? From the image of f. Altogether, guys. Okay. So then what does this mean now? Check. If this function comes here and give us, let's say, y0, having taken here x0, then what would you be saying? You'll be saying f at x0 is equal to y0. So the question now is there a g which can take y0 back to x0? If there's such a function, then we'll say that function is the inverse of f. Such a function will be the inverse of f. So in general, what is this? Check this. Check this. What is this? y0 is f of x. So what is coming out here is going to be g of f at x, giving us back what? x0. Do you see that? So what kind of a function is this? It's kind of a function which you can say is a g after f at x0. And then this function, it seems to be doing nothing. What does it do? It picks x0 and gives back x0. Do you hear what I'm saying? It picks x0 and gives back what? x0. This kind of a composite function here. It picks x0 and gives back x0. Actually, in general, it will pick any x and they give back x. So this function is actually a function which is almost doing nothing. Picks x, gives back x. It's a do-nothing function. Is it an important function? Yes, it is an important function. Do nothing. What do you do? Oh, you do nothing. Then if you are doing nothing, what are you doing? You are resting. Altogether. So, but we're not going to call it a resting function. In mathematics, this kind of function is going to be called the identity function. Identity function. Not the new words you are learning. That will be an identity function. You pick a value, you give back the same value. Pick a value, you give back the same value. So, but check what I said here. I say this, if this is the case, this G will be called the inverse of F. The inverse of F. Notation-wise, we're going to write G equals to F power minus 1. But must be very careful here. When we're talking in terms of function in this context, F power minus 1 is not the same thing as 1 over F, which we know from what? From dealing with exponents. Altogether, it's not the same thing. When we're dealing with the functions, this power minus 1 simply says the reverse function, the reverse process, the opposite process. Am I making sense to you? Okay, good. Now the next thing is example of doing such kind of a thing. Let's have an example of doing such kind of thing. Let's say we're given a function f of x equal to 2x plus 1. We've seen this before. Obviously, this is the function which is going to get 2 to 5. We've done this before. So we're checking for another function g, which will take 5 back to 2. But precisely speaking, we don't know this function g. The question is, how can you determine this function g given this one? Solution. Now we're getting into the process of determining that thing. This is how I will start the exercise, guys. This is how I will start the exercise. I know I'm given 2x plus 1. If you want to write, you can write given 2x plus 1. Now, to determine an inverse of this function, if ever it's there, this is what you can do. You can write a schematical something like this. X is an input, gives out y as an output. But the function we're looking for is the function is going to take y as an input and give out x. That is the step number 0, the initial step. That's what you must consider. What is the next step? Number 1. Once I've done this thing says swap the input to be the output and the output to be the input. Now here, this is the output. If I'm going to swap the output with the input, what am I going to write? I'm going to write x equals to 2y plus 1. Am I making sense? But because of the fact that all functions in this context are plotted on the system of axis x, y, and they're expressed always as y is equal to some f of x. So this g is a y also equals to a g of x, and the x will be coming from the horizontal and the y will be sitting on the vertical. Because of that, we need to make here y subject of the formula. So step number 2, making y subject of the formula. Making y subject. I'll just say y subject for the sake of the fact that I'm lazy to write. Y, making y subject. That it takes us to where? That takes us exactly to solving an equation like 2x plus 5 equals to 17. The things we used here, we're going to use it there. In this case now, we'll be solving for x. Here we're solving for y. So what do? We write this, first of all, I'll say for this one, plus minus 1 on both sides. If I say plus minus 1 on both sides to this expression, what am I going to have? I'm going to have x minus 1 equals to 2y plus 1 plus minus 1. I'm using my properties of numbers, yes or no? Then, what do we have here? This is a 0. But we know that any number a plus a 0 is equals to a. So this is what? This is 2y. And this remains as x minus 1. But we know that if a is equal to b, it exactly means that b is equals to a. So what I'm going to do here? I'm going to write this thing as 2y is equal to x minus 1. As you can see, as I move, there's something I'm basing on to move. You can't just push the pen on paper and hope to do correct mathematics. You must push the pen on paper, justify the move. Even if you don't write how you justify, but in your head you must be able to justify the move. Then after this, I have to divide both sides by 2. Then, voila, I have my x, my y as a subject of the formula. Are we together, guys? Okay. So now I've got two functions now. I've got g of x equals to x minus what? X over 2 minus half. I've got f of x equals to 2x plus 1. Then I have to check this function took 2 to 5. I have to check whether this function is going to take 5 back to 2, question mark. I'm not sure yet, but I've got to check. What I'm going to do, I'm going to say g of 5 and then say 5 over 2. Please leave the calculator, man. Leave the calculator, man. you are throwing stones in your head when everything you've got to use the calculator. Leave the calculator. Then what is this? This is 5 over 2 minus 1 over 2. This is simply subtracting 1 from 5. Do you need a calculator for that? You are subtracting 5 halves, 1 half from 5 halves. So you are simply going to be left with 4 halves. And that is equals to 2. Yes, exactly. This gives us 2. So what are we going to say? We are going to say G is the inverse of F. But when you say G is the inverse of F, we are simply saying F is the inverse of G. So it's a two-way relationship. If I point at you and say cousin, you point back to me and say cousin. All together. So a function, if it has got inverse, it is paired like that in that kind of a two-way relationship. Are there, guys? Questions? Questions? Now, let's check what we said before. Let's check what we said before. We said if we compose these two functions, we must get an identity. So there we have F inverse equals to x over 2 minus 1 over 2. F equals to 2x plus 1. Then let's say F inverse after F. Sorry, F inverse after F. F inverse after, we have evaluated what? F. What do we mean here? We're showing F inverse at 2x plus 1. What does F inverse say? F inverse says whatever I pick, I divide by 2. So 2x plus 1 divided by 2, and then I subtract half. That's the language of F inverse. What does this thing say? Sorry, I forgot to put brackets here. This F inverse after F is picking an x. So when I come here, this is going to be 2x over 2 plus 1 over 2, because this 2 is a common denominator. Is a denominator for 2x, just as it is a common denominator, is a denominator for 1. Minus 1 over 2. Then this is a plus minus a, which will give us what? A 0. Yes or no? And a 0 plus this is going to give us a 2x over 2. And that is a 2 over 2, which is a 1. Then this gives us what? X. So what does it do? This function picks x and gives us back x. So it's an identity function. So those two functions are inverse. So in future, when I say here is x, here is f of x, here is g of x, check if they are inverse. We have got to perform this. But somebody will say, no, maybe it happens this way, on the other side it's not going to happen. Let's check that. F after inverse. F after inverse, which will say F in brackets, inverse of F, brackets, then we say F at what? At x over 2 minus 1 over 2. That's F. Yes or no? That's F inverse. Then F says, I multiply by 2 and add 1. Then F performs this action, multiply by 2 and add 1. If you multiply by 2 here, you get x. If you multiply by 2 here, you get minus 1. If you add 1 here, you get a plus minus a, that's 0. Then it gives you what? X. Are we together, guys? So you see, whichever way you do it, you're going to get identity. I move. Yes or no? I'm now going to move. So whenever I say check whether these two functions are inverses, you've got to compose them. If they give you identity, this is a function ID of x. If id of x, what does it do? It simply gives you x back. This is the function which we have always seen as y is equals to x, which simply means y is equals to f of x. F of x, picking x, giving back x. Am I making sense, guys? Am I making sense? Talk to me. Which part? The one which I did now here. No, I'm not going to explain it now. I'm moving to my friend. I can explain it to you later to you, but I invite you to try it first. Just try to see what I'm doing there, and if you are stuck, I'm just moving. I'm seeing that I'm taking time. Is that right? I'm not refusing to answer you. Try it. Then if you've got a problem, come to me. Is that right, guys? Right. Sorry for that. Can we move? Let's move. Now, if you now decide to plot this function on the system of x's, you will see something very interesting. What are we going to see? Check this. This function, we know it crosses at 1. Let's call this 1. In other words, this is half, this is 1. And this function, the gradient is 2. If the gradient is 2, it means y2 minus y1, I'm revising what you know, over x2 minus x1 is equal to 2. But 2 is a number 2 over 1. It's a rational number, which means for every 1 I run, I rise 2. So here, if I run 1, I'll rise 2. It will give me 1, 2. Then I know that this point is on the line and that point is on the line. Are we together, guys? So roughly speaking, that line will be running more or less like this. If I come to this one, there's a mistake here. I think there's a minus half here. So that's a misprint. Are we together? Yeah. If I come to this one, this line will say I'll cut the x-axis way at minus half. We agreed that our half is that there. That thing, isn't it? And the gradient here is 1 over 2. According to this, our run horizontal is 2, our rise is 1. So run 2 there. From here, 1, 2. And our rise will be 1. 1 will be somewhere there. So which means that line roughly will be running this way. Somewhere there, they're going to cross. Do you agree with me? Okay. This is a rough sketch. Precisely speaking, the graphs will look like this. There they are. I plotted them already. And if you look there, there's a line there. This line is y is equals to x, the identity function. So what does it do? The graph of a function and that of inverse squeeze in between the identity function. Oh, everywhere. This side, the identity function is between the function and its inverse. This side, the identity is between the function and its inverse. Are we together, guys? And together, you can see that they form a body which is symmetric around the identity function. And my compositions for that functions, I did them here. You can check that. You can check this calculation. You will see that's going to give you ID. Are we together, guys? That is very, very important. At that point, I can say we have a good idea of how functions work, how functions interact to produce identity or to produce another function, that is composite of functions. And that marks the end of this part of the presentation. I would like to say thank you for listening. My name is Charles Msipa.